Hey everyone, this is Dr. Matt C. Howard and welcome to week 7 of your Business 255 course. This week we are continuing the study of the relationship between variables. So last week we covered correlation, which was the introduction to that. This week we're going to cover regression. So we're going to talk about regression and the study of the relationship between variables. So no longer the difference between groups, but instead the relationship between variables. So as mentioned, we're going to start with regression with one predictor. That shouldn't say one variable. That should be more precise and say regression with one predictor. So you're not going to see this too frequently in research or practice. Typically, if we have one predictor, we're probably going to do something like a correlation. But this is a good place to start. It's a very good place to start with regression with one predictor. So last week we learned about correlation. We had a definition for correlation. Do you remember what it is? Hopefully you said correlation is used to determine the linear relationship between two variables. So correlation is when you have two variables, typically continuous variables, and you just want to get a general indicator of how well those two variables correlate with each other, how much those two variables are related. Are they weakly related and maybe just have a correlation of something like 0.1? Or are they pretty strongly related and have a correlation of 0.5? And it could be two things like job performance and job satisfaction. It could be two things like height and weight. Just any two variables that are continuous, you could correlate. Regression has a very, very similar purpose. Regression is used to determine the linear relationship between one outcome and predictor or predictors. So when you do a regression, you have just one outcome, you have just one variable that you're interested in predicting. So this might be something like job performance, this might be something like organizational revenue. It's just one outcome that you're interested in, and you have one or more predictors. So you have one or more things you think will predict that outcome. So if we're looking at job performance, you might have one predictor of job satisfaction, or you might have multiple predictors. It might be something like job satisfaction, conscientiousness, supervisor liking, how well someone likes their supervisor. All three of those things could predict job performance. And we could test the combined effect of all three of those at the same time via regression. However, to start, we're just going to talk about regression with one predictor. So an example would be predicting job performance with just measured job satisfaction. So when analyzing just two variables, so one outcome and one predictor, it's almost identical to correlation. So if you understood the material from last week, if you understood correlation, you should be fine with regression with one predictor. So one thing to note before continuing is correlation analyzes and discusses the variables in regards to correlation. Makes sense, correlation. But regression analyzes and discusses the variables in regards to prediction. So whenever you're doing regression, there's an implied message that you're looking at prediction. There's the implied underlying thought that you're looking at an outcome and you're looking at predictors. So with correlation, you just said we're correlating these two variables, but with regression, you have to designate which one is the predictor and which one is the outcome, or which variables are the predictor and which variable is the outcome. So we're now discussing things in regards to prediction. We're not just saying we're correlating two variables, we're saying that we're testing the relationship between an outcome and a predictor or the predictors. So when performing a regression, we must specify which variables that we believe are the outcomes or the dependent variable, and which ones are the predictors or the independent variables, as I just said. So we tend to use the term predictors for our independent variables. So these are the variables that we think influence something else. And we tend to use the term outcomes for our dependent variables. So we tend to use the term outcomes for the variables that are influenced by something else. So predictors do the influencing, outcomes take that influence. Predictors are what cause something else to happen, and then the outcomes are what are caused. So typically we would assume, even though this isn't always true, we would assume that something like job satisfaction is the predictor and job performance is the outcome. So job satisfaction is what has an effect on job performance. It's job satisfaction that influences job performance. So therefore we would say job satisfaction is the predictor and job performance is the outcome. For example, So some students might like visual representations better. So as you can see on the top there, that's a representation of correlation. So with correlation, you can think of two variables, variable A and B, and you can think of correlation as a double-headed arrow. You're just looking at the general association between the two variables, and that's it, nothing more. However, the depiction on the bottom is a depiction of regression. You can think of regression as having two variables and then a single-headed arrow. So you can think of regression as having two variables and a single-headed arrow. So with regression, variable A could predict variable B. And therefore you have a single-headed arrow, you're looking at prediction, you're looking at directional influences, you're inferring that there's some type of causal effect, or at least implying it, whereas correlation is a two-headed arrow. Correlation, you're just looking at the general relationship between two things. So remember, as we move forward, that although we use these terms, predictor and outcome, the same rules of causality apply that we discussed last week with correlation. The same rules of causality apply. That correlation is not equal to causation, and just because you get a significant result with regression doesn't necessarily mean one predicts the other. With regression, you could get a significant result, but if you don't satisfy the other requirements for causality, it might not mean that they're causally related. So for instance, last week we talked about the example of ice cream sales and murder rate, how they're always correlated, but they're not causally related. If we had a data set that had ice cream sales and murder rate, and we did a regression with ice cream sales as the predictor and murder rate as the outcome, our regression analysis will probably give us a statistically significant result. Our regression analysis will probably tell you that ice cream sales is a significant predictor of murder rate. However, that does not mean they're causally related. There's many requirements to support causality. We're probably going to cover them later in the semester. Probably, maybe not, we'll see. But one of those is you have to explain, or you have to rule out alternative explanations. So in this example, you could do a regression, you can get a significant result, but if you don't explain those alternative explanations, such as a different variable predicts both of them, you cannot support causality using regression. You cannot say that the two are causally related, even if you have a significant result. You can say that they're related somehow. You can say that you found a significant relationship, but even though we're using the term predictors and outcomes, and we're using those causal terms when doing regression, you cannot necessarily say they're causally related just because you got a significant regression result. And as mentioned, we might cover that more later in the semester, but that's all we're really going to talk about it for now. And also, as mentioned, regression is most often performed with many predictors and a single outcome, but you can also perform a regression analysis with a single predictor and a single outcome, which is where we'll start. So this is the simplest form of regression. And again, regression with two variables is extremely similar to correlation. It tries to find the linear relationship between the two variables. So whenever you're doing basic regression, you're just trying to find the linear relationship between the predictor or predictors and the outcome. So when it's just one predictor and one outcome, you're just finding the linear relationship between those two variables. More advanced forms of regression can investigate nonlinear relationships, but basic regression just looks at linear relationships between the predictors and the outcomes. So when we did correlation, we saw that this linear relationship is represented by R, or the correlation coefficient. Regression is a tiny bit more complicated, but only a tiny bit more complicated. Regression also tries to find the test statistics that best describe the relationship between the two variables, but regression will provide multiple test statistics. So with correlation, you just had R, the correlation coefficient. With regression, you're going to get more than just one. So the results of a regression analysis can be represented by the following formula. And it's y hat equals beta naught plus beta 1x. So when you're doing a regression with just one predictor, it can be represented by the following formula, which is y hat equals beta naught plus beta 1x. So y hat is your predicted value. So y hat is what you would predict the outcome would be given a certain condition. So that's the result of your regression analysis. Y hat is the predicted value given a certain condition. And then x is the predictor. So x is the number you would enter in. It might be the actual data points you get when you're calculating the regression equation. Or it might be at the end, once you get your regression equation, you could put in a number for x to try to estimate what y would be, or what y hat would be or what the predicted value is given x. So once again, in this equation, y hat is the predicted value, so the estimated value, the value you would predict given a certain condition, and then x is the predictor. So x, when you're calculating your initial regression formula, x would be all the data points you have, or you could type in. And then once you have your equation at the end, you could put in numbers for x to try to estimate what y would be given that number of x you type in. And that might be confusing right now. That might sound weird right now. I don't think I did a great job of explaining it at the moment, but fortunately we're going to come back to this next week. Fortunately, we're going to come back to this concept next week once we know more about regression and we can try to figure out what's going on. So your question you're probably asking right now is, well, okay, if y hat is the predicted value and x is the predictor, what's beta naught and beta 1? Well, when you calculate your regression equation, when you do your analyses in Excel, Excel will give you beta naught and beta 1. So beta 1 is the slope of the linear relationship between the two variables. So beta 1 is what you would multiply by x to get your estimate of y. So beta 1 is the slope of the linear relationship between the two variables, and it's extremely similar to r, or the correlation coefficient. So beta 1 is the strength of the relationship and the direction between your x and your y variable. So it's almost identical to what you would think of as a correlation coefficient. So it's very similar to the correlation coefficient. So whenever you see beta 1, you should automatically think that's very similar to a correlation. That's the strength and the direction of the relationship between my x and my y variable. And then beta naught is the intercept of the linear relationship between the two variables. So beta naught is, if you were to plot it on a graph, where would that line intersect the y-axis at? If you were to make a graph of the relationship between x and y, and you were to draw that line of best fit like we looked at last week, beta naught is where that line intersects the y-axis. Another way to think about beta naught is the value of y hat whenever x is 0. So beta naught, you can think of it as your baseline. Beta naught is the starting value. So if you're looking at the relationship between x and y, beta naught is what y hat would be whenever x is 0. So I don't know if that helps, but let's ask ourselves, what does this mean in practice? That might help you clarify these concepts a little bit. So this is a visual representation of what I was just describing. So let's say that the blue dots are our actual data points, and then we drew that dotted line to depict the regression equation. So we have the blue dots that are actual data points, and then we drew the line of best fit. We drew the line that represents our regression equation in the dotted line. As you can see, the formula right there is the actual regression formula, the actual result we got. We ran a regression on this data. So our regression formula was y, that should say y hat, but I couldn't format it correctly. Y equals 1 plus 1x. So as you can see in this chart, let's start with the beta naught, which is that first one there. As you can see in this chart, we get that from where when x is 0, y would be 1. So when x is 0, y would be 1. So if you look at the left-hand side of this chart, you can see where that dotted line touches the y-axis. It touches it at 1. So that's showing us that when x is 0, y is 1. That is our baseline. And it's showing us our intercept. It's showing us where that regression line crosses the y-axis when x is 0. In this instance, y would be 1. Then the second number you can see in that equation is the number 1. So this is telling us the slope. This is telling us the direction and magnitude of the relationship between x and y. So in this example, whenever x goes up by 1, y goes up by 1. And you get that from the number right there. You get that from the beta 1. That whatever that number is, that's how much y increases for every 1 increase in x. So whatever beta 1 is, whatever that second one right there is in other examples, that tells us for every 1 unit x goes up, that's how much y goes up. So since it's 1 in the current example, whenever x goes up by 1, y goes up by 1. And you can see that on the chart. you can see that we have on the left hand side, when x is 0, y is 1, but then when x is 1, y is 2. When x goes up by 1, y goes up by 1. So when x goes from 0 to 1, y goes from 1 to 2. And you can see that continue all the way throughout this chart. That then when x goes from 1 to 2, y goes from 2 to 3. When x goes from 2 to 3, y goes from 3 to 4. And so on and so on. You could do that all the way through. So once again, beta naught, which is the first one right there, is what y is when x is 0. It tells us what the intercept is. And then beta 1, which is the second one, which is the one that's next to x, that tells us for every unit increase in x, how much y goes up. So it tells us whenever x goes up by 1, how many units does y go up. Let's look at another example. So in this example, our regression equation is y equals 90 plus 10x. So take a minute, pause the video, and try to see if you could figure out how this equation is reflected in the chart. See if you can figure out, guess what I'm about to tell you about the equation. Okay, so hopefully you're able to identify that, like last time, the blue dots were our actual data points, and then the dotted line was the result of our regression equation. So we ran our regression, we got our results in Excel, and then we plotted it in visual format. So the blue dots are our observed data points, and then the dotted line is our estimated regression equation. So in this example, we have beta naught is 90. So beta naught is 90. Can anyone tell me what that is? Pause the video, try to guess yourself. So that's where the that's where the regression line crosses the y-intercept. That's what we have for y when x is 0, or you can consider that the baseline. So in this example, the intercept, or what y is when x is 0, is 90. And you can see that where the dotted line crosses the y-axis. You can see that where the dotted line touches the y-axis. That when x is 0, y is all the way up there at 90. And then can anyone tell me what beta 1 is? Hopefully you said the right answer. It is 10 in this example. So in this example, whenever x goes up by 1, y goes up by 10. And you can see that in the chart. That when we start at the intercept, when we start at x being 0, y is 90. When x goes up by 1, y goes up by 10. So when x goes from 0 to 1, y goes from 90 to 100. And if we do that again, when x goes from 1 to 2, y goes from 100 to 110. When x goes from 2 to 3, y goes from 110 to 120, and so on and so on. So for every 1 unit increase in x in this example, y goes up by 10. Okay, hopefully you understand that. If this is confusing to you right now, it's okay to pause the video, it's okay to shoot me an email, and it's okay to ask me questions. But if you're good with this so far, let's continue. Okay, so here's another example. So this one looks a little bit different. This one's a little bit different. But pause the video, try to see if you can interpret what's going on here, try to see if you can figure out what's going on here, and then I'll tell you the answer. Okay, so in this example we have, once again, the blue dots, which are our data points, but this one looks like more realistic data. This is data more like data you'll see in real life. The prior two examples, the data was in an exact straight line, and that never happens in real life. So in this example, we have more realistic data points. And then we calculated a regression, and we plotted our regression line in a visual format. So in this example, we have the dotted line, which is our line of best fit. That's the line that best describes the data, and it doesn't touch most of the points. It actually touches one of the points. And that's very typical. That's very realistic for real life data. So in this example, we have our data, we plotted our observed data, we drew that regression line of best fit, and then the equation right there is our regression equation. So in this example, our intercept is 11. Y is 11 when beta is 0, and that's our baseline. And you can see that once again in the chart. The dotted line touches the y-axis at the number 11. That when x is 0, y is 11. And also, as you can see, beta 1 is negative 0.9091. Beta 1 is negative 0.9091. So what does that mean? That means in this example we actually have a negative relationship between x and y. The prior two examples were positive relationships, and this one is a negative relationship. And that's perfectly fine. That's perfectly okay. You'll find this quite often. All that means is that whenever x goes up 1, in this example, y goes down 0.9091. So if you ever have a negative beta 1, that means there's a negative relationship. Whenever x goes up, y goes down. So in this example, whenever x goes up 1, y goes down 0.9091 points. And you can see that in the chart, that we start at the intercept. We start when x is 0, y is 11. And then when x goes up by 1, y goes up by 0.9091, close to 1. Then we can see when x goes up by 1, y goes from 11 to almost 10. Then we can see when x goes from 1 to 2, y goes from 10 to pretty close to 9. And then we can continue with that. When x goes from 2 to 3, y goes from close to 9 to close to 8, and so on and so on. It's not exact because we're subtracting about 0.9091 each time, but this is more realistic for what you would see in your results. This is more realistic for what you would see in your data. So once again, in this example, the intercept, or what y is when x is 0, is 11, and the beta 1 is negative 0.9091. And whenever x goes up by 1, y goes down by 0.9091. And that could happen very frequently. Make sure you understand that before continuing with this lecture. Okay, and here's the last example. This is once again more realistic data, more realistic results you would actually see. So in this example, we once again plotted our observed values as the blue dots. The blue dots are our observed values, and we can see that we plotted the regression equation visually. We plotted a visual regression equation. And that's the dotted blue line. So in this example, the intercept, or what y is when x is 0, is 37.333. So that's our starting value, that's our baseline. And our slope, or our beta 1, is 0.303. Our beta 1, or our slope, is 0.303. So in this example, whenever x goes up by 1, y goes up by only 0.303. And that's not that strong of a relationship, as you can see visually. Of course, these are unstandardized results, and we'll talk about the difference between unstandardized versus standardized next week, or sorry, after your test, but we'll ignore that for now. So anyways, so in this example, our beta 1 is 0.303, and that means whenever x goes up by 1, y goes up by only 0.303, and once again, you can see that visually. That we start at 0, x being 0, and y is 37.333. So when x goes up from 0 to 1, y goes up by only 0.303. When x goes from 1 to 2, y goes up again by only 0.303. And we see very little change visually, because that is very little change in this example. So therefore, sometimes your regression equation could give you a virtually flat line if your beta 1 is pretty small relative to the rest of your data. Okay, so long story short, a regression equation tries to find the best values of beta naught, which is our intercept, and beta 1, which is our slope, that allows us to accurately predict y using x. And if we had more predictors, it would be predicting y using x1, x2, x3, x4, so on and so on until we account for all of our predictors. So that's all regression does. It just tries to find the best line of best fit. It tries to give us the line that's represented by the beta naught, beta 1 equation. It just tries to give us the line that best describes our data. So this is just for your knowledge. This isn't going to be on the homework or the test, but one thing you might have asked yourself is, how do we define best? How do we know what best is when we're doing regression? Now, I'm not going to get too complicated about this because I'm not going to test you on it, but this is for your knowledge. This is just for your general understanding. Most often, we define the best as the equation or the line that will give us the smallest difference between our observed values, or our y values, and our y hat, or the predicted values. So it gives us the smallest difference between our observed values, or the blue dot on the last few slides, and our predicted value, which was the dotted line on the last few slides. So it tries to give us the line, or the dotted line we saw in the past few slides, that's the smallest total difference between all of the blue dots and their distance from that line. So typically this is calculated through the following formula, and it's the sum of our observed values minus our predicted values squared. And this is called the sum of squares due to error. So this is, we take the sum of all of our observed values minus their associated predicted values squared. So we sum all the squared differences between our observed outcome values and our predicted values. And this is often called the sum of squares due to error. So pretty much we just try to find the line that has the fewest deviations from our observed values. So let's take the following example. So if we use that last slide we were just looking at before, we would take all of our observed values, we would calculate the difference from the observed value to the dotted line. So we would take the difference from the observed value to the predicted value as determined by our regression equation that we obtained from our analyses, and then we would square them. We would take all those differences, we would square them, and we would sum them. And that's how we get the sum of square due to errors. So we would take these orange distances, and visually represented in this example, we would take these orange lines, we would square them, and we would sum them. And that's how we determine which regression line is the best, or that's how Excel automatically determines it. Is it gives you the line that gives you the smallest possible sum of squares due to error. So if you were to draw any other line on this chart, it would have a greater sum of squares due to error. So what you're seeing right here is the best possible line given that criteria. What you're seeing here is the best possible line that gives us the smallest sum of squares due to error. So therefore, Excel automatically calculated the line that had the smallest sum of squares due to error. And if you were to draw any other line on the prior chart, if you were to make any other regression equation on the prior chart, if you were to do any other thing else on that chart, in this example, straight line, maybe a curved line would do better, maybe a weird shaped line would do better, but we're just assuming we're talking about straight lines for now. But if you were to draw any other straight line on the prior chart, it would have a greater sum of squares due to error. And that's how we define best. And that's how Excel, that's how SPSS, that's how any statistical analysis typically would calculate your regression line, would calculate your regression equation, is it tries to find that line of best fit as determined by the sum of squares due to error. I think that's pretty neat. Our statistics are advanced enough that we can automatically calculate that. I think that's pretty neat that our statistics are advanced enough that we kind of take it for granted that in Excel we can calculate that line, we can figure out that line in a half a second, in a tenth of a second. We can do it just like that. And before that would take hours, maybe even days to calculate that line of best fit, to calculate the line that gives us the smallest sum of squares due to error. But Excel can do it for you instantly due to interesting statistical mathematics. And this is another chart. I'm not going to go into it, but maybe pause the video if you're really interested in this concept, and it explains it to you a little bit more. It will describe some of the features of calculating that sum of squares due to error a little bit more. So that's all I'm going to say about that, but let's continue about the required stuff you should know about regression. So this stuff you should know about regression, this will be on the homework and tests. So regression will also provide us an overall R-squared value. So what does this tell us? What does the R-squared value tell us? It's just like the coefficient of determination. It's just like squaring your correlation coefficient. Our overall R-squared value will tell us the amount of variance in the outcome that is explained by the predictor. So it gives us a general sense of how much variance our predictor explains in the outcome. And as we move on in the later weeks of discussing regression with more than one variable, our R-square will actually give us the amount of variance that all of our predictors predict in the outcome. It actually will give us the variance that all of our predictors predict in the outcome. So that's what the R-square is. We will also get a p-value for each predictor, and most software packages can provide confidence intervals for each predictor. So we'll just focus on p-values in this class since it's a pretty introductory class. So for each predictor we'll get its own p-value, and that will tell us whether that predictor is statistically significant in predicting the outcome. So the p-value that we get for each predictor tells us whether each predictor is statistically significant in predicting the outcome. So we could do a regression with 3, 4, 5 variables, and we would get an individual p-value for each of those variables, and it might be 2 of them are significant but 3 are not. It might be 1 of them are significant but 4 are not. So we can determine whether each of our predictors are statistically significant. At the moment, that's going to be pretty easy since we'll just have one predictor. We'll have one p-value for the intercept, one p-value for the predictor, and it'll be pretty easy to determine whether your predictor is statistically significant. Also, most software packages will provide standardized and unstandardized betas. We'll talk about these after the next test. We'll talk about the differences between standardized and unstandardized betas after the next test. Just know that we'll be discussing the unstandardized betas today, and that's typically what I'll ask you for in your homework assignment and the test up to this point. Also, most software packages will give you the t-statistics, p-values, and r-square values. You need to report the p-values, you need to report the r-square values. You need to just be aware that you can get the t-statistics that go into calculating your p-values. Okay, so that's all theoretically about regression with two variables. So hopefully you understood that. If you didn't, make sure you pause the video, make sure you shoot me an email, because that's all I'm going to tell you theoretically about regression with two variables. That's all I'm going to expect you to know at the moment. I feel like that was a lot of dense information. I want you to be able to digest it, interpret it, figure out what it means. And then once you feel comfortable with it, let's go ahead and talk about how to calculate it in Excel. Okay, so let's talk about calculating a regression with one predictor in Excel. So this is what our data might look like. As you can see, we have job satisfaction and job performance like we usually do. And we have job satisfaction in column A and job performance in column B. And in this example, job satisfaction is our predictor and job performance is our outcome. So like most other like most other analyses that we've learned in this class so far, we start by going to the Data tab and we click on Data Analysis. If it's not there, you need to go back to week 1 and activate your Data Analysis tab. We go to Data, then we go to Data Analysis. With that wonderful window that pops up, we're going to click on Regression and push OK. So click on Regression and push OK. And then it's going to tell us to input our Y range and our X range. So we're going to start with the Y range. So the Y range is our outcome range. The Y range is whatever we want to designate as our outcome variable. So we're going to want to tell our Y range as our outcome variable. So we're going to click on that button that's highlighted right there. And we're going to go ahead and highlight our outcome data. We're going to go ahead and highlight the data that is for our outcome variable. So go ahead and highlight that and then push the other button that's highlighted. Also, as a side note, it depends on your preference. You could go ahead and highlight the label there. You could go ahead and highlight the label if you choose, but in this example I didn't. But go ahead, highlight the data, include the label if you want to or not, and then push the other OK button. And then go ahead and click this other button to input the X range. So the X range is going to be our predictor range. The X range is going to be our range for our predictor variables, or variable in this example. So click on that button. Highlight the data for our predictor or predictors. So go ahead and highlight that data for job satisfaction in this example. And also, I'm going over this just to show you what it looks like. This should be the same example data set that I provided in the guide, in my email, and in the comment to this YouTube video. So if you want to go ahead and follow along, you could download that data, but I'm just trying to give you an idea of what it looks like first before you go on to the guide and before you do the guide. But anyways, so in this step we're telling it our X range, we're telling it our predictor data, so we go ahead and highlight the job satisfaction data. So this is extremely important. So before, if you highlighted the label for job performance, if you highlighted the label for your predictor variable, you need to go ahead and highlight the label for your, if you highlighted the label for your outcome variable before, if you highlighted the label for job performance, you need to also highlight the label for your predictor variable or variables. You need to go ahead and highlight the label for job satisfaction. So before, if you highlighted the label when you indicated where your data was, you need to highlight the label again. But before, if you did not highlight the label, you now need to not highlight the label again. You can't highlight the label for one and not the other. You have to either highlight the label for both or highlight the label for none. That's extremely important. But regardless of what you do, highlight it and hit the OK button that's highlighted right there. You should get this window right here. And this is also extremely important. If you did not include those labels when you highlighted your data, just go ahead and push OK. If you didn't include those labels when you highlighted your data, go ahead and push OK. But if you did highlight those labels, if you did include the labels when you were highlighting your data, make sure you click on the Labels button in this window. Make sure you click on that button right beside the word Labels in this window. So if you did not highlight your labels, push OK. If you did highlight your labels before, push the Labels button here and then push OK. That's extremely important. You will get incorrect results if you don't do this correctly. So make sure if you did include your labels before, you push that Labels button and push OK. So with that, let's continue. So you should get a lot of output that looks like this. Hopefully if you're using the guide data set, it gets the same numbers, but don't worry about that if you're not doing it. Just try to pay attention and get an idea of what this looks like first. So the first thing we want to look at is right down here where it says coefficient and right next to the intercept. So that is our beta naught. So where it says coefficient and then right beside it, it has our intercept, that is our beta naught. So in this example, we would say our beta naught is 4.053. So in this example, our beta naught, where it says coefficient, that means beta coefficient. Right beside where it says intercept, that's our beta coefficient for our intercept, or our beta naught. It is 4.053 in this example. So that's where we would find our beta naught at. The next one, as you see right here, is 0.654. So this is where we would get our beta 1 from. So it's in the coefficient column, which is our beta coefficient column. It's beside where it says x variable. So in this one, we just had one predictor. So our x variable is our one predictor, which was job satisfaction. So we would then know that our beta 1 is 0.654. So from these two pieces of information, we would know that the regression equation from this example is y hat equals 4.05 plus 0.65x. So we would say that our beta naught, or our intercept, is 4.05. So we know in this data set we're looking at, our starting point, or our intercept, is 4.05. And we know that the slope is 0.65. We know that that starting value, whenever we do our, we know that x would go up, that for every one that x goes up, y would go up 0.65 in this example. So once again, our beta 1 is 0.65. So in this example, we know for every one x would go up, y would go up 0.65. So that's what our results look like. It's kind of interesting. Our intercept 4.05, our slope 0.65, so our starting point 4.05, and then whenever x goes up by 1, y goes up by 0.65. Okay, so right here what we have highlighted is our t statistic for our predictor variable, our t statistic for our job satisfaction predicting job performance. That's 4.482, so that's good for you to know where to find, but I'm not going to focus on it too much. Next is our p-value, and this is extremely important. So in this one, this is our p-value for the relationship of job satisfaction predicting job performance. So right here is our p-value for the predictive ability of job satisfaction predicting job performance. And in this example, it's 0.0001. So is this statistically significant? Hopefully you said yes. This is statistically significant because the p-value is less than 0.05. So this is statistically significant because the p-value is less than 0.05. And you see that because we have the p-value, it's 0.0001, and it's on the x variable row. It's on the row for our predictor. It's on the row for job satisfaction. So from this, we know that job satisfaction was a significant predictor of job performance. We know that job satisfaction is a statistically significant predictor of job performance. And then the very last thing I want you to pay attention to is the r squared, which is provided up there where it's highlighted. So our r squared is 0.427 if we round, or it's 0.43 if we round to just two significant figures. So we would say our r squared value is 0.43. So from this, we would know that job satisfaction explains 43% of the variance in job performance. So from this, we would know that job satisfaction explains 43 of the variance in job performance. So altogether, we got our regression equation, which I believe was 4.05 plus 0.63x. We got our p-value for job satisfaction predicting job performance. So we found that job satisfaction was a statistically significant predictor of job performance, and you can interpret that very similar to a correlation in this example. So we know that there is a significant relationship between the two. So we know that job satisfaction is a significant predictor of job performance. And lastly, you know that job satisfaction explains 43% of the variance in job performance because of our final R-squared value. So those are the main pieces of information you should be able to obtain whenever you do a regression analysis. Those are the important things you should know, and those will be the things on the homework and the test. So that's all for this lecture. Make sure you go and do the guide. Make sure you do the guide that will help you learning this analysis. But otherwise, that's all I really want you to focus on this week. That's all I really want you to know for this week. So make sure you do the guide, make sure you can understand the guide, and as always, make sure you can do the homework assignment. As always, if you have any questions, if you have any comments, please let me know. I'm always happy to help. But otherwise, do the guide, do your homework, and also don't forget there's a test next week. There is a test next week. So make sure you're prepared for that, make sure you're ready for that, and please make sure you read my email early next week. The test next week will be on Friday. If you're not available to take the test on Friday, please let me know as early as possible. I might not be able to reschedule the test if you let me know at the last second, so please let me know as early as possible if you're able to take the test, if you're not able to take the test on Friday. Otherwise, I'm going to assume that you can take it, and if you don't take it, then you get a 0, but please let me know as soon as possible if Friday does not work for you. Otherwise, thank you for listening. I will talk to you next week, and I hope you prepare yourself well for the test next week. Thank you.